Welcome back, teachers. I want to talk about Chapter 6, Section 6-2. We're talking about addition and subtraction of whole numbers, and we're talking about mixed numbers. And this is Part 2 of our conversation. So if you haven't watched Part 1, go back and watch Part 1. And let's get going. So the additive inverse property. So for any rational number AB, there exists a unique rational number negative A over B called the additive inverse of A over B. So notice what happens. If I take A over B and add it to negative A over B, I get 0. But the additive inverse has to be commutative as well, so that we get negative A over B plus A over B, and that's also equal to 0. We could make up an example to make it more clear. If I were to take 1/2 plus a negative 1/2, we know that equals 0. And it's also true that negative 1/2 plus 1/2 equals 0. It's that simple. Okay? Now, properties of addition for rational numbers really match very well those of the properties for integers. Okay, so if I read this, properties of the additive inverse for rational numbers are analogous to those of the additive inverse for integers. Okay, so remember we had negative of a negative A, or the opposite of A is another way to read that. That is just A. It's true for rational numbers as well. And remember the distributive property? It's like a distributive property over addition. If you have a negative in front, then you could take that inside, and that negative A plus a negative B, exactly the same thing with fractions. We have the addition property of equality. If A over B and C over D are any rational numbers such that A over B equals C over D, so we're saying two fractions are equal, and E over F is any rational number, then you can add that same rational number to both sides of the equation. And you often need to do this when you need to solve a rational equation. Let's talk about subtraction of rational numbers. If A over B and C over D are any rational numbers, then A over B minus C over D is the unique rational number E over F. So E over F, picture that as your answer. Okay, now if you'll remember when we worked with integers, subtraction was defined to be the opposite of addition. So A over B, remember this is your minuend, okay, and this is your subtrahend. Okay, if we have an answer to our subtraction problem and it's E over F, then you could say A over B, your minuend, is equal to your subtrahend plus that answer. Really, subtraction is the opposite of addition. Now, if A over B and C over D are any rational numbers, then what are we saying here? A over B, notice that's on both sides, and we're subtracting the same number on both sides. Okay, now I prefer that written as, I'm looking at the way this has got it written, this would be A over B minus C over D is equal to, oh no, this is not what I thought it was. They're changing subtraction to addition and changing the sign of the next number. Remember doing that with integers, so ignore what I was saying over here. That is not the theorem I thought that they were giving you. If A over B and C over D are any rational numbers, then A over B minus C over D equals AD minus BC over BD. What is that? That's that definition that we were using to add fractions together. This is the same thing, but we're subtracting fractions. And let's do a few of those problems. Okay, so if we use that definition that they gave us, 5/8 minus 1/4, and if we use that definition, we could say 5 times 4 minus 1 times 8 divided by 8 times 4. Simplified, 5 times 4 is 20, minus 1 times 8 is 8, and 8 times 4 is 32. We know 20 minus 8 is 12 divided by 32. And then we could reduce this or write this in lowest terms or completely simplified by dividing these both by 4. Is that the greatest common divisor? See, 4 divides into 12. We could say 4 times 3. 4 divides into 32. That's 4 times 8. The 4's cancel, and we get 3/8. I have that typed up. Here we go. They say 5/8 minus 2/8 is 3/8. Why does theirs look so much simpler? Well, because they notice that 8 and 4 have the least common multiple of 8, so they simply multiplied by 2 over 2 right here. And so that's going to be 5/8 that didn't change minus 2/8. That's the one we changed. 5 minus 2 is 3/8. Now how about the second one? What could we do with the second one? We haven't discussed yet a method for adding and subtracting mixed numbers. That is something that we need to discuss, but it is not on the table right now. So what we need to do is change these to improper fractions. How do you do that? If you would like to use the method where you write 5 1/3 as 5 plus 1/3, and then find a common denominator, and then use your addition of fractions and add that together, or you can use the cute trick where you say 5 times 3 is 15, and then you add the 1 to get 16/3. That is faster for most folks. 2 times 4 is 8 plus 3. That's minus 11/4. Now, the greatest common divisor between 3 and 4, also called the greatest common factor, is 1. So that definition that we use where we cross this way and multiply, 16 times 4 minus cross this way, 11 times 3 divided by 3 times 4 is just as good as finding a common denominator. 16 times 4 is 64, minus 11 times 3 is 33, 3 times 4 is 12, and then if we take 64, subtract 33, we get 31 over 12, and 31 and 12 don't have any common divisors, so 31 over 12 is lowest terms or completely simplified. And then the typed up version of that gives us that. Now what have we not done? And here's the convention, which I personally suffer from sometimes not remembering. But if you start with mixed numbers, your final result should be in mixed numbers, and I want to warn you, in the homework, most of the homework answers that I've read say write your answer as a simplified fraction or mixed number, which means no improper fractions. So 31/12 is what we had, just to let you see, there's my 31/12, but we didn't write that as a mixed number. We need to do is use a method to change 31/12 to a mixed number. Remember, we did that 2 different ways. One way was the reverse of writing a mixed number as an improper fraction, which is probably a little bit confusing and awkward. Another way is we could divide 12 into 31. This is what I see most students doing. This is certainly what I do. We know 12 divides into 31 2 whole times. 2 times 12 is 24, our standard long division algorithm. Then 31 minus 24 gives me a remainder of 7. And now I know my answer is the quotient plus the remainder over the divisor. 2 and 7/12. If you need that written down, that's quotient plus the remainder. I'm going to abbreviate over the divisor. Now, why did I not write the plus in between? Because when we write mixed numbers, we don't actually put plus in between, but really there's a plus there. We have some more practice problems. We want to add or subtract, write your answers in simplest form. So reduced form, simplest form, that does mean the same thing. Now we could use our definition here. We do know that 2 and 3 have no greatest common divisor. Well, they do, but it's just 1. So in that case, I could use my definition for addition again, and I could say that this is equal to, cross this way, 3x, cross this way, plus 2x divided by 2 times 3. Simplified, that would be 3x plus 2x over 6. But 3x and 2x are what we call like terms. I can add those together to get 5x over 6. And that does not simplify any more than that. That is in simplest form. If we look at their result, see it's the same thing, just a lot neater. Now the next problem B, there is a greatest common divisor other than 1. They both have an x in common. So rather than doing that cross trick that we just did, what I'm going to do is write the problem again, 1 over x with a little bit of space minus 1 over 2x squared. This x is already included over here. So what I would like to do is multiply the fraction using the fundamental fraction theorem and multiply the same value on the top and the bottom. And so we don't have 2, so I need a 2, and we're missing an x, and that's going to make that an x squared. And I have to multiply by this on top as well. Now that's going to give me 1 times 2x is 2x minus 1. Notice this denominator right here is 2x squared, and they match. And that is the final result. Now, why can't I cancel this 2 and this 2 and this x and one of those x's? Because you can't cancel part of addition or subtraction. If you ever try to do that, what you're really supposed to be doing is using the distributive property to factor. And I can't factor. There are no common factors here. So this is as simple as this problem gets, and you will see their typed up result there. All right, let's talk about estimation with rational numbers. Many of the estimation and mental math techniques that are used with whole numbers also work with rational numbers. Estimation plays an important role in judging the reasonableness of computations. So here we go. A 6th grade class is collecting cans to take the recycling center. Becky's group brought the following amounts in pounds. About how many pounds does her group have altogether? So remember, we're doing an estimation here, not an actual calculation. They want us to use front-end estimation and then adjust by using 0, 1/2, and 1 as reference points. So what do they really mean? So front-end estimation is where we handle these numbers in the front. Sometimes they were in the hundreds place. These are just whole numbers. So we're going to add those numbers in the front first. You'll notice that's what we do here, 1 plus 3 plus 5. And then the adjustment. Now, to explain what this adjustment is, let's go back and look at what we've got going on. So they want us to adjust by using 0, 1/2, or 1. So when we take a look at 1 and 1/8, the 1/8, does that adjust closer to 0, closer to 1/2, or closer to 1? In my argument, 1/8 goes closer to 0 than 1/2. Remember, 1/2 would be 4/8. Okay, now 4/10 is very close to 1/2, which is 5/10. So I'm going to adjust that one to 1/2. 7/8, hey, 8/8 is 1, right? So 7/8 is going to adjust close to 1. 6/10 is just a hair over 5/10, which is 1/2. So remember, we did the front end, 1 plus 3 plus 5. And now we're going to do the adjustments by adding these values, which is 1/2 plus 1/2 is 1, plus this one is 2. So it's like 1 plus 3 plus 5 plus the adjustments are 2. So that would be 4 plus 5 is 9 plus 2 is 11 would be my estimation. So if we go back and look at their result, again, the adjustments is what we did as well. And that was the 2 added to the whole numbers in front, which was 9. And there's the 11 that we just talked about. Now here they want us to estimate the following, but they didn't talk about adjustments at all. So think about this just in terms of rounding to whole numbers. So 27 over 13. Now that's an improper fraction, right? Which is a mixed number. We could rewrite that as a mixed number, but say we want to do this really quickly. Well, how about this? 26 over 13 is 2, right? Because 26 is double of 13. So 27 over 13 is an approximately 2, plus 10 over 9 is approximately 1, And if we add those together, we get about 3. Right? So that's a quick estimation technique. Let's try to get down here. 3 and 9/10. Well, 9/10 is almost 10/10. So 3 and 9/10 together is about 4-ish. 2 and 7/8. Well, 8/8 is 1. And then we have this 2, so that's about 3. And then 11/12 is nearly 12/12. So that's 1. And then again, all this is an approximation. 4 plus 3 is 7 plus 1. It's about 8. Okay? Let's see the way they handled it. Sure, so 2 plus 1 is about 3. Notice they use the double wavy lines. Gotta get my pen to working. There we go. I tend to use a single wavy line, but a double wavy line is probably more accurate. And then the second answer, that's exactly what we did as well. The 3 and 9/10 is about 4. 2 and 7/8 is about 3. And 11/12 is about 1. So, hopefully this gives you the skills to get through this section 6-2. Again, we are working with addition of fractions, which are rational numbers, subtraction of fractions. We're working with mixed numbers, changing mixed numbers to improper fractions and improper fractions to mixed numbers. And finally, estimation. So if you have any questions, please let me know, and I'll see you back for section 6-3. Have a good day.